You're actually staying.
Okay, will be the next session. The first speaker is Professor Michael Butler from the University of Southampton. We will talk about proof with event B Rodin.
Thank you. Thank you for the invitation. Although I was not directly involved in the ProCoS project, I did attend a ProCoS workshop in 1994, so over 20 years ago, and that was in Lundby. And at the time, I was doing a postdoc in Turku in Finland with Ralph Back and Kaisa Sari and other people. So Kaisa and I went to this workshop, and I spoke about work that I'd been recently completed for my PhD, which was around action systems and the link between action systems and CSP. And I felt a little bit out of place because the approach I was talking about was very much what Cliff called the positive improve approach. So we have an abstract model and we give a refined model, and then we try to prove that the refined model is the correct refinement, as opposed to using some refinement algebra to everybody else at the time seemed to be working on a more algebraic approach. And I did actually then in Finland work with Ralph Back and other people on a refinement algebra and implementing a tool to support refinement algebra. And we called it the refinement calculator. It was precocious on this, called it the refinement calculator. And it worked for very small examples. And it used Hall as an underlying proof engine. So every refinement step that you applied to a specification was proved under the hood using Hall. But I really never figured out how one could get that to scale. Okay, so because one of the problems was that the menu of possible transformations just kept growing and growing and growing as you looked at more and more interesting problems. And the whole sequence of interactions with the tool was sort of lost. Okay, and actually the persistence of that is really important. So it's not just the end result that's important, but actually how you get there, because actually you might want to change how you get there. So anyway, I sort of went back to the positive proof approach, and partly that was because also while I was in Finland, I met Yves Sorensen at another workshop in Denmark, which was a Nordic workshop in Denmark, and he persuaded me to start using the B toolkit. The B toolkit, of course, was again a verification, proof obligation based approach, and actually back in Finland I taught a course on B in order to learn it. And then I began to get quite excited about B because I could see the connections between B and my own work on action systems and other people's work on action systems. Another workshop that I attended while I was in Finland, I met Jean-Ramon Abrial. That was the steam boiler workshop in Dagstro. And so we had done an action system version of a steam boiler, and Jean-Ramon at least was very excited by that. And as a result of that, I also started working with Jean-Ramon. And then jump back 10 years with Jean-Ramon and also Cliff at Newcastle and other people, we started working on this Rodin project. And the idea was really to move, at least our different people may have had different views of what the project was about, but our view was moving what we now call classical B away from just software and reasoning about software to reasoning about systems. There's a lot I could talk about, but Jonathan explicitly asked me to talk about proof in Rodin and B, and I'm obeying orders. But interestingly, so from my point of view, actually a lot of the work that I did for my PhD, which was all on paper and theoretical, is now realized in Event B and the Rodin toolkit, so that's quite nice. So very quickly, what is Event B? So it's a state transition model like ASMs, B, BDM, Z, and so on. Uses set theory as a mathematical language. That's really important. That sort of gives it a lot of the richness. The refinement supported by Event B is very much influenced by Ralph Back's action system. So data refinement, one-to-many. So a model is a collection of guarded events, guarded actions. One-to-many mean that a single abstract event can be refined by multiple different refined events. We can introduce new events in a refinement corresponding to stuttering steps. And as I said, the idea was to be more suited to system-level modeling. I'll give you an example of what I mean by system-level modeling, as opposed to just modeling software systems, which is what classical B was designed for. The proof method, positive proof, as I said, so proof obligations generated from models. Invariants play a really important role in those proof obligations. So it's really about invariants, the proof method. And then the tool, the rollout tool, essentially is a proof obligation generator and proof manager. So I'd say I use the term proof manager advisedly. So you shouldn't think of it as a theorem proving system. It actually uses other theorem proving systems and manages the use of those other systems. So I'll talk a little bit about that as well. So what do I mean by system level? So here are some examples of invariants of models that we've done of systems. So the first one is the landing gear for an aircraft. So it's one of the case studies from the ABZ conference last year. So it simply says if the landing gear door should be open, so that's the door for the landing gear. Second one is from railway system, not the passenger. If the signal for a particular route is green, then this is, here we see some user set theory. So the blocks associated with that route are not occupied. So the square bracket is a relational image. The image of the route under the blocks relation intersection, the occupied sections is empty. And the last one is an access control system. So if a user is located in a particular room, then the set of activities that take place in that room is a subset of what that user is authorized to do. In other words, that user has sufficient authority to be in that room. So let's just give you a feeling for what I mean by systems, modeling systems, and reasoning about systems. The rollout toolset is community effort. So here are the main contributors, some companies and some universities. So Sister Ellen Pierce here in French companies, universities you'll have heard of. And the development of the rollout toolset was supported by a succession of European Union projects. So it started in 2004, the rollout project, which is where the name of the tool comes from. So the name had a certain cachet, so we decided to keep the name for the tool after the end of the rollout project. The deploy project was a larger project, actually, which you had more industrial partners and more industrial deployment. And then the most recent one is a smaller project called in France. Right, so on to the meat of the talks. So the two key things I want to talk about. One is, so I told you roughly what it is we're proving. It's essentially proving that one machine is a refinement of another machine. And we typically do that as a chain of refinements. So one of the key ideas is actually keeping those proof obligations as simple as possible in order to make it easier to prove them. And there are a number of techniques that are used in event B to do that. Now, I'll quickly go through those. And then I'll talk about what kind of theorem proving tools are used to actually discharge those proof obligations. Okay, but two things are really important and go hand in hand. So one is techniques that keep the proof obligations as simple as possible, and then using the appropriate theorem proving and model checking technology. So the first one, of course, is abstraction, and Cliff gave a very nice example of that yesterday in the list reversal. The idea is that you have an abstract as a model as possible that still allows you to, for example, capture the key steps in an algorithm, and you reason about it at that level, and then you do further, for example, data refinement, data verification. Cliff used the example of a list reversal, and so it was later, at a later stage, you verify to heap structure, for example. Let me give, I'll go through the others later. So here's an example, another example of using abstraction to keep the proof obligation simpler. It doesn't mean that overall your whole proof effort is easier. It's essentially, it's about layering the proof effort, and if you like, a heuristic that I like to follow is tackle the most difficult bit first, and the most as abstractly as possible. So here's an example of that. This is just a diagram that's like a map of how refinement might work. So it's an example of a replicated database that uses a two-phase commitment protocol. And this rectangle at the top, I can't point to both at the same time. So the rectangle at the top of the diagram represents an atomic event, okay, so which is commit, and it's very easy to specify that abstractly, atomically. And the abstract model just contains a single database, so let's pretend we have a single database rather than lots of copies. And then in the refinement, we introduce multiple copies of the database, one at each site. And so we don't simultaneously update all those databases. So the database updates are become asynchronous. And here's the next level down is introducing just enough events to represent the asynchrony in the updates. And then later we can introduce further events. So for example, if I go back, the global commit is this key step. It's the point at which all of the participants decide that they should update their databases. So that the solid line there means that that's actually a true refinement of the abstract event. And the dashed line, those other events are like new events, doubly expected. And we have enough event structure to be able to prove the connections between the single abstract database and the multiple copies, the replicas at this refinement level. And that's actually the most difficult part in terms of the invariants that you need and trying to prove those invariants. And then we can deal with other parts. We're actually, for this particular example, the proof obligations are simpler and easier to prove. But by working at a more abstract level on the difficult part, so there's less noise, the mathematical structures are simpler and so on. And we can do further refinement. So here's further refinement where we're actually we can then start to distinguish events that occur at different parts of the system, different components of the system. So that's what this colors mean. So what this diagram also shows is that syntactically, your specification is very atomized, if you like, and some people dislike that about event B, because rather than having something like a structured program with sequential composition and loops and conditional statements, you just syntactically describe the individual steps. And so on each of these rectangles will just represent individual steps. The advantage of that, of course, from a proof point of view, is that all of the, so that's the next technique, if you like, because all of these events are syntactically separate, all of the proof obligations are localized to individual events or pairs of events. So it's pairs of event if it's a refinement obligation. And again, that's leading to simpler proof obligations. So this is a screenshot to illustrate that. So here's a screenshot of the Rodin tool. So we have a model. Maybe you can't see the details on the right-hand side. On the left-hand side, a list of proof obligations. I'll zoom in on the proof obligations. So all the green proof obligations are proof obligations that have been proved, and the red one is one that has not been proved in this case. What I want to show you really is that, so in this particular model there are 4 invariants, and essentially for each event, so for example we've got the initializations, we've got add authorization invariant 1, add authorization invariant 4. So essentially for each invariant in each event we're going to have a proof obligation. Some of them there will be trivial, so they won't appear as a proof obligation. And the reason is because that event does not modify any of the 3 variables of that particular invariant. Right, so the next technique is about decomposing the data refinement proof obligation, and this is really key for simplifying the data refinement proof obligations. So this is a bit technical. So it's just describing the general definition of the data refinement proof obligation supported in the NP. And this is forward simulation for those who know about the difference between backwards and forwards. This is forward simulation. ProCoS does not support backwards simulation. So the top we've got general form of an abstract action A and a refined action C. And the abstract action has a guard and an action. And the action in its most general form can be defined by a predicate on the default vector of variables. So it's a predicate called SA on A and A prime, where A are the variables that are modified. And similarly for C. And then typically the gluing invariant will be in two parts. So there'll be an invariant in the abstract model, which is called I, free variables A, and an invariant in the refined model, which is J, and it has free variables A and C, so the variables of the abstract model and the variables of the refined model. The data refinement proof obligation then, it's a bit ugly. So all of the proof obligations are sequenced with some hypotheses and a goal. And the problem with this proof obligation is the goal, of course. So it may look innocent enough on the slide, but of course the SA and the SC and the GA and the GC and the I and the J are big long lists of predicates. Okay? And the problem is the existential quantifier, because what we want to be able to do, of course, is to split all these conjuncts into separate proof obligations. Now you can pull out the GA because it doesn't have A prime as a free variable, but the others you can't. And so the technique that's used is what's called a witness predicate. And the witness predicate is local to an event, so it's not a global predicate, so each event can have its own witness predicate, so it may be different for different events. And the witness predicate essentially allows you to then break these large data refinement proof obligations into lots of smaller proof obligations. So that you end up with just a single existentially quantified goal, which is typically the W, the witness predicate, is a lot simpler than the gluing invariant. In fact, quite often it's an equality that provides an exact witness. And of course, also remember the SA, the I, and the J, the GA are typically conjunctions, so those again can be split into lots of smaller proof obligations. So once you remove the existential quantification, you can then simplify all of those goals, and split all those goals. So here's an example of a witness. So we have an abstract model where we have a variable which is the set of all of the used values used to identifiers. Right? And we have an event which is choose a fresh value. And the guard is choose an X which is not already used and add it to the used set. And in refinement, we replace that by a counter. And when we want a fresh variable, we just increase the counter by 1. And so the witness predicate is an annotation within the refined event. So the witness is that the abstract X is the current value of counter. So by providing that witness, then the data refinement proof obligation can be decomposed into lots of smaller conjuncts. And the last technique, not necessarily, these are not necessarily the only four, but these are the key four ones, is using theories. And of course, this is just standard idea from mathematics. So you capture certain structures, mathematical structures, and operators on those structures, develop proof rules about those structures. That leads to simpler models, simpler proof obligations, essentially raising the level of abstraction of your mathematical language and your reasoning. And so there is, this is a more recent addition to the program toolset, is support for defining new theories. So the built-in mathematical language is quite rich, so it's a lot of set theory, relational algebra. But you can also now, for example, define polymorphic data types, polymorphic operators, and and proof support for that, so rewrite rules, inference rules. There's an induction rule if it's an inductive data type. And then, so some of the theories we've developed, the typical things, list, chains, trees. So in working with Alstom on railway interlocking, developed essentially a theory of interlocking and trains moving around, interlocking of networks and trains. And that led to, so we had an initial model where we didn't use the theory. It's doable, but it's quite complex and complex proof obligations. By using the theory plugin, by developing abstractions of typical operations, essentially operations on graphs, and providing proof rules for those. That led to simple proof obligations, and of course a lot of reusable theories that could be reused across different events and different abstraction rules. We also recently developed a theory of real numbers and continuous functions, so we could even start to play around with modeling and reasoning about hybrid systems. That's very early stages. Right, so those are the sort of techniques that are used in the event-based language to support, if you like, simplification of proof obligations to make the proof more tractable. Then the tool set, so it's not just about verification actually. So the verification part is about proof obligation generation and proof management, as I said already. In an industrial setting, model validation is really key, it's really important. So does the model actually accurately represent the system that either exists or that we want to build? Simulation, animation, graphical animation, so there's support for building a graphical representation of a particular kind of system. Railway system, again, is a typical example. So we have a graphical representation of a railway network with trains moving, and that's controlled by an event-based model. Co-simulation is a recent addition, so where you can have an event-based model with a discrete controller and a continuous model of a plant we use a language called Modelica. It's a simulate-like language. And again, that's really useful for validation of from a formal point of view, validation of your discrete event model. For certification, requirements traceability is really important. And again, the tool supports requirements traceability. By requirements, I mean natural language requirements. And another class of functionality that's supported by Rodin is what I call model transformation. So, for example, we have a graphical representation of event B, which is called UMLB, supports class diagrams and state machines. And again, that's appealing to people in industry. And the transformation that we support, of course, is that those models get transformed into event models, and we can apply all the reasoning techniques to those event models. So UMLB has a notion of refinement, for example. So a notion of state machine refinement, which is essentially introducing hierarchical state machines. So different hierarchical levels correspond to refinement levels. There's actually quite a nice correspondence between refinement and hierarchical state machines. And also model to code or model to assertions. So for example, a PhD student who's generating Daphne assertions. So Daphne is Rustam Lego's verified programming tool from event-based models. A little bit more about the verification. Key feature is the proof manager. So the proof manager in Rodin constructs proof trees for each proof obligation. It uses automatic and interactive modes. So there's an interactive prover where you can drive the construction of the proof tree. Or you can define tactics, and there's some default tactics that come with the tool, of course. So there's a very standard tactic language to adapt the proof manager. The proof manager at each step will call reasoners, and reasoner will either discharge the goal or break the goal into sub-goals, so maybe rewrite the goal or split the goal and so on. So there's a collection of reasoners, so a little bit more about that. So there are some built-in simplifiers, rewriters, and some built-in decision procedures, but we also make heavy use of other, what we call plugins that use other proof technology. And in fact, the one that we seem to be having most success with at the moment is using SMT. So there's an SMT plugin that transforms proof obligations into SMT format. Atelier V is the ClearC's tool for the V method, and it has a prover that has developed over actually a couple of decades, and that's available also as a plugin. Matthias Schmalz at ETH has developed an Isabel plugin, and again showed success in terms of being able to discharge proof obligations that, for example, Atelier V couldn't. And associated with the theory, the ability for a user to define new theories is a theory-based reasoner, so it applies the inference rules and rewrite rules within the theory. And actually, for a particular proof obligation, you don't need to just use one of these tools. So at any point in the proof, so as you're going down through the proof tree, you can call any of these tools. And you define a tactic that can call any of these tools. So another feature that's important is model change. So it's never the case that your model is right first time. I'll repeat that. It is never the case that your model is right first time. For all sorts of reasons. So one is because it's cannot be verified. So you need to change it so that it is correct. But more commonly is because you misunderstood the requirements, or the requirements were misunderstood. And now what you don't want to do is have to reprove everything every time you make a change to a model. So there's some support for sufficiency comparison between all of the existing proofs that you've done and the new proof obligations that result from a change to the model. And even simple things like renaming. So it's quite common that you might want to change the name of a variable. What you don't want to have to do is redo all the proofs just because you changed the name of a variable, right? Another feature is, so I said this, as well as using deductive proof, we use model checking. So ProCoS was developed by Michael Ushel at University of Dusseldorf, and that supports a number of features. So it checks for invariant violations, for deadlocks, for proof obligation violations. So the invariant violations is doing a reachability check, and it uses constraint logic programming. And the nice thing about abstract models in event V, where you're using set theories, there are a lot of natural symmetries. And that's exploited in the model checking. So within this environment, we can use theorem proving model checking on the same models and different theorem proving systems. You can adapt your tactics and change them and so on. So rather than me telling you about some of the industrial successes, I invite you to take a look at presentations from an industry day that we had last year as part of this advanced project, where some of the industrial partners talked about their experiences of using Rodan. And one of them, so two of them actually, AWE and TELUS, were not part of the project. So they're adopting Rodan by themselves, paying for that themselves. And AWE, for example, found that SMT gave them dramatic improvement in proof. So that was really nice. I'm getting very close to the end. So here's an interesting map, which is all of the countries that have downloaded at least 1,000, the tool 1,000 times in the last 5 years. And it's spread quite far, but no, it's clear. Obviously, ACL2 is. There's some surprises, like Vietnam and Saudi Arabia, Algeria, and Malaysia. Lots of people contributed. So these are all. I keep adding to this whenever I give a presentation, and hopefully that list will keep growing. So that's the end.
Yeah. Okay, questions?
Your proof manager, maybe I missed something.
you have these many plugins.
Yeah.
Does it do intelligent selection or?
No, there's no intelligence. It's just within the tactic, you can say, call this, call SMT, call it TAUV. If it succeeds, then stop. If not, try this. There's no intelligence. It's very brute force.
So you have this example with the replicated database.
Yeah.
So for these sorts of systems, there are numerous correctness conditions out, serializability, opacity, linearity, and so on. When you say you do a proof by refinement, what is it that you're actually proving?
So proving, I guess, what you might call one copy rule, which is that let's pretend that it's just a single database, and everything we do can be seen as a correct refinement. Everything we do to a replicated database can be seen as a correct refinement of that. And it includes...
So where do you specify this one copy rule? So
at the abstract level. So, I mean, I didn't show you the 11b, but there's just a single, there's a very simple variable, which is a function from object to the value of the object. And the commit event just updates some of the values of some of those objects atomically. It's very simple.
So you don't do eventual consistency?
Well, that comes out in the refinement.
The idea of having various theorem prover plugins is an attractive one, of course. But how do you assure that the different theorem provers are all using the same logical foundations? I mean, you might...
We do our best.
Okay.
So it's an entirely valid question, but it's a sort of pragmatic approach that we take. And there is, if one really cares about that, then there's work to be done there.
Right.
At the moment, it's sort of fairly pragmatic.
We and Cambridge are working on translating ACL2 proof obligations to Hull and vice versa, but you can't do everything in either direction because of the differences in the logics, and it's delicate. But, and if you're not careful, you end up believing you proved a theorem, but in fact, there's no single theory that is the theorem of.
So one reassurance is that we can try to use several different tools to prove the same thing, and that maybe increases our confidence.
Okay, thank you very much. Our next speaker is Dr. Rod Chapman from Progeny Code Limited. And we'll talk about, are we there yet? 20 years of industrial theory improving with Spark.
Okay, thank you. Thank you all. It's a great pleasure to be here. I too am a ProCoS outsider. I was not involved with ProCoS originally, so I'm slightly confused as to why I was asked to be here in the first place. But nevertheless, I thought it would be a nice idea to come along and talk about what we've done over the last 20 years or so, possibly on a similar path to what ProCoS set out to do. And I'll tell you where it all started and give you some history. Mainly, I'll try and tell you about some real projects, some real industry stuff that was being built over the last 20 years, and to try and give you an idea of when we say, oh yeah, we proved something about some program. Well, what have we proved? What have our customers been proving? And how have we done in terms of scale and depth of the proofs that we've been attempting, and how far have we come? Also, talking about projects gives me an excuse to just show you pretty pictures of aeroplanes and so on. So we'll see how we go. It all started about 28 years ago, and we've had the stubbornness and good fortune to somehow still be doing this. Maybe we should have given up years ago and gone home. The first definition of the Spark language is dated March 1987, which seems like a shockingly long time ago. Yesterday we saw lots of pictures of people that have been involved in ProCoS, so I thought I would introduce some of the protagonists in this work. The chap on the left is Professor Bernard Calais, who was at the University of Southampton, shockingly in the Department of Electronics, of all things. And he was the driving force behind the sort of founding of the big idea of this project. In the middle, that's Trevor Jennings, who was the co-author of the first language definition. Trevor retired last year, and he was still working on it. He's been involved for nearly the entire history of the project. On the right is Peter Amy, who took over running the team from Bernard when Bernard retired. Unfortunately, Peter is no longer with us, I'm afraid to say. I haven't been involved after that for some time as well. When I say, by the way, if I say we did this or we did that or us, I'm referring to my predecessors and my colleagues at Praxis and Altran and everyone that's worked on Spark team, not just these guys in particular. Warren and Wayne, yesterday and this morning, were kind enough to mention Spark. Unfortunately, they were talking about the one on the right, not the one on the left. The one on the right is a heavily defended trademark of Oracle Corporation and is an instruction set architecture of a RISC microprocessor. The one on the left is a programming language, and that's the one I'm going to talk about, so please don't confuse it with the one on the right. We do have to make that point now and again. Okay, so yes, as I said, what have we been proving? What's been proven? Why? What was achieved? How big are the programs, and how deep are the proofs? More importantly, perhaps, what have we learned from these years of doing it? I'll concentrate on projects that have deployed the technology. Some of those projects are projects which have been built by my colleagues at Praxis, but some of them are projects that have been done out there in industry by other companies like Rolls-Royce or BAE Systems or Lockheed Martin and others. I'll have a bit of feedback as well based upon that experience, what we learned and what we did with the technology as a result of those experiences. Perhaps a little bit of commentary on our interaction with the so-called freely licensed and open source software community as well, which has been useful in the last 5 years or so. So the big idea was to design a programming language and a set of verification tools, but specifically design it for so-called high-integrity applications, most of which it turned out at the time were embedded in real time as well. So there's a lot of overlap between the embedded real-time systems community and the high-integrity community. So we're mostly talking about small black boxes that are flying aeroplanes or doing things like high-grade crypto communications, that kind of stuff. The biggest design goal of the system was soundness. That was non-negotiable. We wanted the system to offer a verification environment where you could actually really trust the result of the thing and say, yeah, that says I've got no bugs in my system, and I want to be able to ship that with some confidence. That took priority over completeness. Completeness means the lack of false alarms or false positives from the verification system. So it's very easy to do a verification tool that says, warning, your program might have a bug. And you just print that 1,000 times. That's not much use. We want it to be fast. I'll talk about speed later. It's very important. Modularity is actually the key to efficiency. Modularity is very, very important in language design. If we can have separate compilation of programming languages, well, why can't we have separate verification? Why do I have to read in the whole program to do useful verification? Is that not a flaw in the language design? So modularity is a big deal. And depth, meaning I want to be able to verify non-trivial properties, interesting stuff, not just have I indented my code by 3 spaces or 4 spaces, because that's a bit dull. It's important, it's what we call a broken window. It's something that you should probably have a basic discipline, but I want to prove stuff like freedom from buffer overflows and safety and security concerns and so on and so on. An important constraint that the team set themselves was, for God's sake, don't try and write a compiler for the language. Spark, the A, stands for Ada, and there were a significant number of commercial Ada compilers around in the late 80s. We did not want to compete with the business of compiler writing. That's come up with a verification slide and undefined things in them where they say, hey, why don't you just leave that up to the compiler? That's really annoying if you're trying to build a verification system. So achieving soundness in the face of multiple compilers is actually quite a trick. And yeah, we started with the 83 version of Ada, and basically you simplify, subset, add contracts, go around again, do some research, make it bigger, go around again, do some research, make it bigger, and Moore's law comes along and gives us faster computers every year. So the scope of what we could do grew as computers got faster, and you kind of go around this loop of trying to make the language more powerful and more useful, and possibly selling it now and again to people. So the first project that came along that actually decided to use this, in 1986, British Aerospace built this thing. Some of you might go, oh, that's a Eurofighter. It's not. That is an experimental aircraft program. That's an EAP, of which exactly one was built. Is that right, Peter? Just the one of these flew, I think, in August 1986. This was a technology demonstrator for various advanced features of aeroplanes, including the fact that this airframe is aerodynamically unstable. It does not fly without a computer system balancing it in the sky at a high rate of knots. This brought to the fore the fact that to build an aircraft like this, software would be critical all over the place in such an aircraft. So that was an interesting idea. If I'm allowed to just jump forward 28 years and imagine several million lines of however much code gets written and lots of bits of metal get banged together, you get some of those. And there were soon to be 5 squadrons of these in operation. There were 4. I think a 5th squadron is being stood up next month. This is a Typhoon FGR-4. I think this is out of 6th Squadron at RAF Lossiemouth. So these can be seen flying over places like Cornwall or Scotland or wherever they appear to turn up. There's also a squadron at RAF Coningsby, I believe. So there is a very large amount of software in that airframe doing all sorts of critical stuff. We don't know exactly what. Almost all of it is written in Spark. Almost all of it. I don't know exactly what proportion. But a lot of it is there, and this was the first big project that kind of booted the product into life, if you like. It generated some money and some revenue, so Bernard and his colleagues set up a little company in Southampton, and this sort of forced Spark into commercial use, if you like. The positive side of that is that it became a commercial product and it was able to be developed. The negative side of this, looking back, was that the team basically lost touch with the academic community. The ProCoS project and all the wonderful things that were going on at the time, and since for about 10 years, Spark sort of disappeared off the radar of the academic community. I think that was our fault. We were just too busy trying to survive and stay in business that we kind of disappeared off into industry and we're never seen again. So let's move on. The next project that was interesting, this is the first project that tried to, in quotes, prove something useful using the theorem proving technology. It was a project called SHOLIS, the Ship Helicopter Operating Limits Information System, which is a right mouthful. Basically, this is a system which assists the crew of a ship with the safety of helicopter operations. It's best illustrated by that. The thing underneath is a Type 23 frigate. I believe that's HMS Monmouth. The thing on top is called a Merlin or an EH-101. That's very big in comparison to that. That flight deck is not as big as it looks. Trying to put one of those on one of them is difficult and skillful. If the ship is rolling and pitching, and ships also do something called heave. I don't know if you knew this, but heave is vertical, Z-axis movement. If a flight deck of a ship heaves significantly, it creates an enormous updraft. And that's very bad if you're trying to hover a helicopter over the thing at the side of the land or something. So the SHOLIS system actually goes here, just inside the hangar, and assists the crew in determining what isn't safe to do with the helicopter. So we developed that system. To give you an idea of the environmental constraints, that's a picture of the flight deck display unit undergoing its icing test. So it's being blasted with freezing cold salt water for hours on end to check it still works if it's exposed to freezing cold salt water for hours on end. And so on, it's running away there, you can see the SHOLIS display. So in terms of proof, what happened? It's about 27,000 logical lines of code in the application software. It produces about 9,000 verification conditions out of our VC generator. Our theorem prover at the time in 1995 really didn't do too well. It only managed to prove 75% or so of those automatically. And that left muggins here, mostly me, I'm afraid to say, with an awful lot of manual work to do to prove the remaining 2,500 manually with an interactive proof assistant. Some of you may have tried if you've used ACL or Isabel or one of the other interactive, sort of big interactive proof tools. It's kind of like playing one of those old text adventure games from the 1980s. Do anyone remember Zork or Hitchhiker's Guide to the Galaxy? You type "Go North" and the prover says you are in a twisty proof full of lemmas, all of which look the same. You type hit conclusion 6 with axe and lemma 5, but it says you are in a twisty proof full of lemmas. And, you know, days and weeks go by attempting to discharge these proofs, and it's not much fun, it's expensive. One thing we did note, though, is that the unit testing of this software was subject to a significant test program. The unit testing appeared to be completely useless, because after it had been proven, the software was exhibiting a very low defect rate, where the unit testing basically didn't turn up anything and appeared to be a waste of money. So that was an important discovery. We published that in 2000. That result, and since then we've actually adjusted our process. We actually try to get rid of unit testing on Spark code these days because it just ain't worth it, because the defect rate isn't there to be found. Next interesting project, new RAF toy, C130J. You can tell it's a J because it's got 6 blades on the propellers, not 4. It's an easy way to tell, at least when it's standing still. This was developed by Lockheed Martin in Marietta in the States. Their initial development used Spark, but only did what we would call the kind of basic level of analysis. They did the subset enforcement, and they did data flow and information flow analysis on the code, which gets you certain properties, but they didn't attempt, in quotes, proof. They didn't use the field improver to do anything initially. What was surprising was that even code that had been through that level of discipline was substantially easier to test than code that hadn't. And indeed, there was a substantial saving reported in the test budget. And it appeared to hit this sweet spot of the fact that actually software is of quality and discipline. Later, after the software was actually cleared for flight, there was an analysis of the software carried out in the UK on the aircraft by various people, including what was then Aero Systems in Yeovil and Kinetic, Peter's colleagues at Boston Down. The result was largely unsurprising. The Spark code was an order of magnitude better than most of the other software on the aircraft on average. The ADA was an order of magnitude better on average than the C and all sorts of other languages on the aircraft. There was no correlation between residual defect density and level A and level B, which is a bit worrying, because to hit level A for flight, for avionics software, you have to do a lot of extra work. You have to do structural coverage analysis to a certain level and all sorts of things. That appeared to make no difference to the residual defect density of the software. This data is in Crosstalk Journal. A chap called Andy German reported this. It's available online. So that was an interesting experience. Feedback from those projects, we urgently needed to improve our theory improving capability. That was clear. We couldn't, be putting up with 75%. We needed to do much better. The real big hits were automatic unwrapping and instantiation of universally quantified hypotheses in conclusions. That's because of arrays, because an array type in Spark. As soon as you hit an array, you get yourself universally quantified hypotheses and conclusions in the VCs. You've got to know how to unwrap them, find the correct instantiation, fiddle about, take away the number you first thought of, and improve those automatically. Reasoning about modular arithmetic turns out to be important. That crops up all over the place in embedded software. You're doing modular N arithmetic a lot in embedded software, doing crypto, doing buffering, doing all sorts of stuff. So we needed to improve that. And basic range tracking of integer expression. So holding on to symbolic ranges for integer inequalities turned out to be important. So we implemented that lot, and that made a big difference in about 2002. We found the biggest impact really on completeness was not necessarily a technical thing. The biggest impact on completeness of the theorem improving software, of the theorem improver, was the quality of the software in the first place. Well, yeah, but what does that mean? We had to learn how to write proof-friendly software, and we didn't know how to do that in 1990 or 1995. It took about 10 years to work out how to design for proof so that we knew the software would be amenable to a high level of automation. That took quite a long time. A big issue is to do with post-condition explosion, which means having the technology support proof involving state abstractions and refinement of types. So things like being able to prove with private types, and treat them as private at one level, but in one package body, you see all the detail, rather than having the detail everywhere, which just leads to an explosion. Next project that was interesting was called Tokeneer. This was a project funded by the NSA in the States to do a demonstrator of high security software development. This was a complete process done by Praxis. We started with the requirements using a Michael Jackson style requirements engineering approach, specification in Z, code in Spark, so we kind of pulled out all the stops on this one and delivered it. It's pretty small, it's only about 10 kLOC. Much better completeness than the theorem prover this time, up to about 96%. And eventually this project, the NSA, 5 years after we delivered it, the NSA allowed us to release this project for public study, and some of you I know have looked at it. Jim's worked with it, some of you. And it's been a vehicle for teaching and research ever since. We're really quite proud of that. The biggest project I would like to mention is NATS IFACS, the Interim Future Area Controller Tool Support Package, another terribly arduous acronym. This is a set of tools which provide support to air traffic controllers working at NATS's centre in Swanwick in the UK. En route means aircraft above 4,000 feet, so it's nothing to do with it's nothing to do with airports. It's not to do with approach. It's en route, which means above 4,000 feet at the moment. It provides flight script management, but importantly, trajectory prediction. That means predicting where the airplanes are going to be in the future. And conflict detection means, are any of the aeroplanes going to be too close together in the future, where too close together is defined by a certain regulatory regime that requires separation vertically and longitudinally of any pair of aircraft. So here are some happy looking air traffic controllers sitting at a workstation, a sector control unit. This is the operations room at Swanwick. And they have these very large radar screens. You'll see here this funny thing. This is a wooden board with flight scripts on it. IFACS replaces the wooden board with a screen with electronic management of flight scripts. That's one of its big functions. The other thing they get is an extra window that looks like this. This is called the separation monitor. What this shows you is time on the x-axis, where 0 represents now, and time increasing towards the right on the x-axis is number of minutes in the future relative to now. On the y-axis, we have separation in nautical miles, and an icon here, for example, means that in 11 minutes' time, these two aeroplanes are going to be 4 nautical miles apart, with the arrows pointing the same way is what's referred to as a catch-up interaction, meaning two aeroplanes moving in roughly the same direction but getting closer together, they're catching up with one another. This would indicate to the controller that they need to take some action, because the line at 5 nautical miles is one of the separation requirements. So if there's an interaction coming at 4 nautical miles, the controller is prompted to do something to make those aircraft not interact in that way, and so on. So you can see other types of interaction here indicated on the graph. It provides the controllers with a view of the future that they cannot do in their head. Most of the controllers can't see this far ahead, so it provides them with extra vision, if you like, into the future to plan aircraft movements ahead. One of the biggest impacts of the system is that the aircraft can be routed through a sector more smoothly, meaning with fewer climbs, fewer descents, fewer turns. A really big impact of that is that it saves fuel for the airlines. It saves lots of fuel, lots of money, and also results in far less carbon dioxide being pumped into the atmosphere. There's a significant environmental impact of this system, is that the smoother routing of aircraft is actually a good thing for everybody involved. This has been fully operational since December 2011, so if you've flown in or out of the UK in the last 4 years, you've been a customer of this system. The functional specification happens to be written in Z. It's a very large one, possibly one of the largest specifications written in Z that we've ever seen. Almost all the code is Spark. It's big. It's about 250,000 lines of code, logical lines of code. So stuff that actually does something. It is proven, not very deep, it's proved what we would say type and memory safe, to use posh programming language designer terminology. Basically, it means that for any input data and state, it never becomes undefined, it never crashes, and it never raises any exceptions. So it never goes wrong, as I think Robin Milner once said. Type safe programs don't go wrong. So this software basically doesn't crash, and we reconstruct this proof regularly. Scale-wise, we're doing 153,000 verification conditions on that software. That was a particular build of the software that's about a year old now, of which the theorem prover, with a bit of assistance, automatically is hitting nearly 99%. So that's pretty good, and that comes from learning how to design the software properly in the first place. That's not by just brute force in the theorem prover. That's learning to design well, which is important. With a bit of help, we pump in some user-defined lemmas into the theorem prover. That actually gets to 100%, so the proof is discharged completely every night. But I say every night, actually, wouldn't it be better if we could do now? Wouldn't it be better if we could do coffee break? Instead of having to wait overnight to get the proof? Well, why not? All you need is lots of CPU cores. With 153,000 VCs, I can have 153,000 CPU cores. That's one each. Why not? You might think that's an outrageous number of CPU cores. I proposed this to a friend of mine who works at Google, and he shrugged and said, "Oh, only 100,000 processor cores? I could deploy that tomorrow." You know, that kind of processing capability is not out of the question in this day and age. So why not run it all in parallel? Well, that works well. I'll skip that one since I'm running out of time. I'll skip that. In terms of performance, what we're actually running here is when IFAX was at its peak, it had about 50 developers. Well, if you've got that many developers all wanting to prove their code all the time, what they're supposed to do is do the proof stuff before they can even commit the code to the CM system. A change is not supposed to be committed unless the theorem prover says it's okay. What you really want is performance now, and we want the performance to be so fast that we wean people off the temptation to compile it and see what it does, or test it, you know, that kind of thing. We want the proof tools to be used in preference to compile and test. That means it's got to be pretty quick. So what we did was implemented a cache. Basically, we have a distributed persistent cache of all the proofs that are constructed by the project every day. And then whenever the theorem prover wants to construct a new proof, it goes to the cache and says, "Oh, we've seen this one before." The cache says, "Yep, there you go, there's the answer." This gets us down to 15 minutes to reprove 250,000 lines of code. That's coffee break kind of time, which the engineers really like, because they can just go, "Yeah, prove everything. I'll just check I haven't screwed it up. Okay, I've only changed one package, but prove everything." They go get a coffee, they come back. Working on one package, we're pretty close now where they just press the button and they get feedback straight away. That's because of modularity in the language. With the modularity, the independence of proofs work so that you can prove one bit and know you haven't messed up anything else. One more project I'll bring to your attention is MUON. It's rather hard to pronounce. This was a great surprise. The University of Applied Sciences in Rapperswil in Switzerland, actually funded by a company called Secunet, who are a German company who have a relationship with the German security agency, the PSI. They funded this work, and these guys at the university actually produced a separation kernel, but written in Spark, which seems amazing. We were very surprised. We would have thought this was impossible 5 or 10 years ago. It's very small, only 2,500 lines of code, but they've managed to prove the thing is basically type safe and crash proof. And this runs on 64-bit x86 multi-core platforms, so something like a Core i7, one of the big modern Intel chips. This implements a low-level separation kernel. And much to our surprise, they were able to do it in Spark, which was very odd. Just to mention, this is most of my talk's been a bit wincy. This is the bit that's a bit withery. What's going on next is that we threw it all away and started again. We realized that the technology we had, theorem proving technology, the VC generator from the original work, basically we hit the wall. We just couldn't go any further with that technology. So we decided to start again. And we've started again with Ada 2012, which includes contracts as part of the native language. The contract system in Ada 2012, for those of you familiar with Eiffel, looks a lot like the kind of way it looks in Eiffel. So we finally caught up in Eiffel. But all the tools are new, so we reuse the entire GCC compiler infrastructure, the front end of the Ada compiler, and it gives us a whole massive, loads more stuff in the language. So generics are finally in, thank goodness. So for those of you that program in C++, templates in Ada, they're called generics. Generics with contracts and concepts is actually a very powerful thing. There's a formal container library. It supports object-oriented programming with dispatching and list of substitution principle and all that stuff. So it's all much bigger, honest. One interesting thing about it is that the contracts can be proven, or you can execute them, like in IFOL, or both. If you're feeling particularly paranoid, you can prove the contract's correct statically, but then compile them into your program and run them as well, just for sort of belt and braces approach to do things. So it offers some interesting some options. I suspect that's nearly the end. That's about the technology. We've rebooted the technology. We're using SMT, CC4, Altergo, all the sexy fashionable stuff under the hood that you expect. There's a bunch of references if you want to know more. Thank you all very much for listening. Thank you.
We have time for a couple of questions. Yes?
Do you have a kind of a guide to how to write verifiable programs?
Yes, we actually ended up creating a training course in how to do it because we realised our customers didn't know, universities weren't teaching it. So now we ended up creating an entire training course for how to do it. And we've taught quite a few people. Neil from AWE, is Neil still here? You've been on the course, haven't you, Neil?
Yes.
Yeah, there you go, there's one. I wish it was something I could write down in 5 pages in a big sense, but it's basically good common or garden software engineering sense. Stuff like low coupling is a very good idea. Very careful selection of abstraction of states and types is a very good thing you have to do. Avoidance of complicated language features is a good idea. It's all common or garden stuff, but encoding it in a way that we can teach did actually take up a lot of time. Yeah.
Okay, one question long.
There's one there.
Just to follow up on, are there any, do you have any published materials of that type thing that interested people could go and read? Or is it just the training things that you sell?
Quite a lot of the training material now is online. I can point you at it. There's sort of online videos and stuff. We've got a bit more advanced with the multimedia recently. There's some videos online, yeah. I can point you at where it is.
Okay, thank you.
Everything. Another question.
Been updated for, there's a Spark book requirements.
The book, John Barnes' book is not completely up to date with the 2014 version of the way that I've just mentioned. And a pair of authors, John McCormick and I have to remember, I think it's Patrice Chabat in the States are working on a new book that describes the Spark 2014 version. That will be published later this year, I believe. Or just look online, it's all freely openly available. I mean, the language definition, everything, it's all there. The tools are openly available as well, so just go download it.
Yeah.
Okay.
Thank you very much.
Sorry, what do you want? It's okay. Okay, good, right.
Okay. The last speaker in this session is Professor Ursula Martin from the University of Oxford. Title is What Have You Learned About Proof?
Right. Well, that was going good. So, well, it's very nice to be part of this amazing occasion. I was part of ProCoS in the beginning, dragged into it by Cliff, I think. Where's Cliff? I was working in Manchester at the time, and there was Howard Barringer part of ProCoS as well. Sort of. And Doug Edwards, sort of. Yes.
He used to turn up to the meetings.
He used to turn up to the meetings, yes. Well, and it was a great opportunity. It was the first big EU project I've been part of. Unquestionably one of the best organised. I still remember the meeting where Linus got us all together we got us all together to plan things, and he had, I don't suppose the acetates still exist, do they?
Well, yes.
He stood in front of an old-fashioned acetate projector, drawing boxes and arrows and saying, right, you're that box and you're that box, and bingo, we had a proposal. And the other thing I remember was, this was, when did the proposal actually go in? 89, 90? Yeah.
88. So
88. It was, this was before we had the World Wide Web, younger people. There was a time before the World Wide Web. And I was very impressed with the sense of style, by which obviously there was a deadline by which this thing had to be delivered in Brussels. And somebody was deputed by these to fly from Copenhagen to Brussels to hand deliver it. I don't know who that person was, but I lost somebody. Anyway, that style, I thought. And, yes, I can carry on about style. I was impressed by the sense of style. Some wonderful meetings we had. The meeting on an island, Bornholm, where we were all told to arrive at a ferry terminal in Copenhagen. We went on a night ferry to Bornholm. It was probably dirt cheap because we took over a boarding house at the very end of the season, but it was a rather wonderful atmosphere. Right, so what am I going to talk about? What have we learned about proof? Well, you take your mind back to what proof meant in 1988. Well, we've heard a lot in the past day and a half about different aspects of that. But I suppose one of the things was that working in formal proof, well, particularly in a department like Manchester, full of real chaps who build things, it was a bit odd being, what on earth was all this formal proof stuff? And when you look now at the impact of formal methods, programming principles, proof, or whatever, and you start to talk about people now in leading university departments about what's going on. Well, perhaps I just came up with one slide to indicate the kind of presence that our field now has in the academic world. This is a rather good theoretical programming principles, logic and verification group. I can say that because a bunch of them used to be colleagues of mine at Queen Mary. They're at UCL, which is, it's about a mile that way, isn't it? UCL, yes. And look, here are all the theoreticians. Oh, wait a minute. Jay Hubbard, joint appointment with Microsoft Research. Byron Cook, joint appointment with Amazon. Peter Ahern, on leave at Facebook. Robin Hirsch. Juan, on leave at Google. And David Pym, it doesn't say Hewlett Packard, but David spent a couple of years at Hewlett Packard. This is academics at the heart of some of the biggest software companies, the kind of companies, of course, none of the Microsoft Research was founded in 92, 93, something like that. These companies did not exist in 1988, but now these are the companies that impress our students. Wow, you get a summer internship with Amazon, or Google, or Facebook. Boy, do I want to do a student project with these guys. The impact is really quite remarkable, I think. You're from UCL, I probably left off some people too.
No, that's pretty much everyone. of the faculty members.
Of the faculty members, yeah, that's pretty much. So, proof has had real impact. Companies like these companies are picking up on what this community is doing. And if you look in particular, this is of course the kind of talk that Peter Ahern should be giving. And according to Facebook, Peter wishes he was here. But what is Peter Ahern doing at Facebook? Well, Peter, when he was at Peter has this meeting is clear. How many talks have referred to Peter Ahern and separation logic? A good few, yes. Well, Peter Ahern and his mates at Queen Mary a few years ago did a startup called Monodics, which built a tool called Infer, which used separation logic and a sort of modular approach to static analysis. And one day, summer 18 months ago, I was minding my own business, going around IKEA actually with my nieces. And I got this phone call from Peter saying, top secret news, but it's going to be announced tomorrow that Facebook have bought Monodics. My nieces were dead impressed. One's a singer and one's a doctor, but the idea that I had a friend who just sold a company to Facebook, and you might think that big company buys startup, you might think that Peter and his gang were then have a life of luxury sitting in the sunshine somewhere. Not a bit of it, they're having a life of luxury sitting at the core of the engineering activities in Facebook London, which is up the road just behind Euston somewhere. And you go visit them, there they are, their stand-up desks. There they are, with their tools running on, as part of Facebook's software process. To look at an idea of the size and scale of Facebook, nearly 1 billion daily logins, 1.9 billion mobile users, and there's a very nice paper that they've written about the challenges of doing what they do in Facebook, and in particular, drawing attention to the difference between things that run in the browser and things that run on mobile. Things that run in the browser, Facebook themselves can continually update the software without any interaction with the user. Things that update on mobile, the user has to download the app or download the updates to the app, and Facebook don't have any control over how often they do that. But Peter's paper explains how they are running. It's completely the opposite of the dream perhaps we had at the start of ProCoS. So you do everything in a unified way, you specify, you verify, you build. Because what's going on in Facebook is they're rebuilding twice a day. And they are running their tool on, this is Peter's seminar, not mine, so obviously. They're running their tool. They're running their tool on every one. Certain categories of programming changes every time they're made. A completely different model from the model that perhaps one sometimes thinks about. And perhaps that's one of the things we've learned about proof. Proof doesn't change, but the way in which you use it, the environment in which you're using it, changes all the time. And people like the Monadics team are taking advantage of that by seeing how to exploit the ideas that we've been developing in the community over many years. The other side of this picture is Peter and co having a little brag because they found some bugs in OpenSSL. So that's one thing we learned about proof. What else have we learned about proof? Another thing we've learned is we've learned about large computer mass proofs. This is Thomas Hales. Thomas Hales is really, I think, the person who brought to the serious mathematical community a sense of the power of formal proof. This is Thomas Hales with a pile of tennis balls. The tennis balls are exhibiting the Kepler conjecture. The Kepler conjecture says essentially, if you want to pile up tennis balls or cannonballs or oranges in the most efficient way possible, this is the way, not some other strange, complicated way. The obvious way is the best way. Doing a computer proof of that turned out to involve verifying a whole bunch of extremely fine inequalities. But eventually, after 15-year, I think, effort, they managed to do it. Computer proof is also becoming acceptable to the mathematical community. I mean, it used to be the case that, yeah, we could work away very hard at computer proof, but you go and talk to the mathematicians down the hall and they would just laugh at you. Take you very seriously. Well, that's changing too. Tim Gowers is a very influential mathematician based in Cambridge, Fields Medal winner. He blogs a lot. His blog is very influential in the mathematics community. And what he's talking about here is somebody using a SAT solver to, this is a result where they thought they'd got the best possible bound on something, a 1124. And blow me, a couple of clever guys in Liverpool, Konev and Lisitsa, went away and threw a SAT solver at it and proved that the mathematician's guess was wrong. And of course, they had the assistance of their university press office in explaining what it was they'd done. The negative witness is probably one of the longest proofs of a non-trivial mathematical results ever produced. Its gigantic size is comparable with the size of the whole of Wikipedia, which is, you know, it's like the size of the Isle of Wight, or it's a new measure, or the length of a London bus or something, the size of the whole of Wikipedia. So one may have doubts about which this can be accepted as a mathematical statement, as a proof. But then here's Gowers, you see, the opinion former, saying, I personally am relaxed about huge computer proofs like this. Which is not the thing the mathematical community was saying 20 years ago. It is conceivable they made a mistake, but that's true of conventional proofs as well. So, it's acceptable. It's extremely hard work. Fly-spec, which is the proof of Kepler's conjecture, 11 years. It's extremely hard work. And how you organize that work can get pretty complicated. So this is the credits for Fly-spec. They're using a bunch of different systems, a bunch of different teams. Mark Adams is a name up there. Mark Adams, who is off back working for Ultron at the moment, Rob told me. What was Mark Adams doing? Mark Adams was organizing an army in, somebody mentioned Vietnam earlier on. And said, well, it's rather curious, there's all this interest in Vietnam. Well, there's all this interest in Vietnam because Mark was organizing an army in Vietnam to do this proof. Tom Hales worked out that his NSF dollars would go rather further in Vietnam than they would back home. But just the whole business of how you organize a proof like this, is how you maintain consistency. I mean, this is an 11-year effort. You can start off terribly optimistically and then discover 9 years in that some component you're relying on is just having existed one half-dead machine in the basement. There's a lot of planning, engineering, thinking about how to do all this. Another wonderful achievement is Georges Gontier. Georges Gontier organized and proved something called did a formalization of the proof of something called the odd order theorem, which is another major achievement in mathematics. It's a 600-page maths paper. The proof was already out there, but Gontier and co. did it. It took them 6 years, almost full-time work. It was a team of, a sort of core team of 4 or 5 people at Microsoft, and then various other summary people. So again, hugely hard work. But we know it's feasible. We now know we can do it if we want to. So, well, there are many other things we've learned, but I now want to say a little bit about my own project, what I'm thinking about now. I've done all kinds of things since the ProCoS days, including going off into the dark side and becoming a university senior manager, but I saw the error of my ways and came back to research about a year ago. And I started looking at this question of the environment in which our formal proofs sit. And the slogan is mathematics as a social machine, a combination of machines and people and machines to produce proofs. Because however you look at what's going on, yes, you have your formal proof, but that's sitting in some context of people who want the answer, people who are developing the proof, and that may be and that may be the kind of context that Rob was describing in the previous talk. It may be a very different kind of context of the Facebook guys, or it may be the context of the mathematical community who've kind of realised that okay, this thing is might be quite useful and it's acceptable. They suddenly really figured out what to do with it. So that's what this project is about. And to try and understand that, of course, you need to try and understand the larger process. Now, this was something that people were starting to think about back in the day in ProCoS. This is a paper by, is Debbie still here? Hello, yes. This is a paper from 1993, Formal Aspects of Computing 5. I mean, that's another thing that started about the same time as ProCoS, 1988, I guess. And the influence of serious journals in identifying and shaping a field, and that was Cliff and Derek. Sorry, I'm having a senior.
John. Yeah.
John. That was Cliff and I've got that right, wasn't it? Cliff and John set this up. And here we are, still going strong, still highly respected. Whatever metrics you want, you know, all aspects is delivering on it. But the paper that Debbie wrote was highlighting exactly this problem. That yes, you see the finished proof, and it's absolutely wonderful. But where did it come from? How did you put it together? The whole process of proving, including all the dead ends and false starts, is swept under the carpet, making it difficult to know what's going on. The picture on the left is a book that's just been published by Cedric Villani, talking about this process of proof. He won a Fields Medal a couple of years ago. Actually, there was a great. None of you, of course, were listening to the radio at 9 o'clock tomorrow morning. Yesterday.
But we might be.
But you might be. Well, that's something else that hadn't been invented in 1988 was you can listen again online to Cedric Villani talking on Radio 4 yesterday morning. Very. Where do proofs come from? Well, and of course we know that if you look at, as Debbie's paper said, if you look at the finished article, this is Chunke Andrew Wiles' proof of Fermat's theorem, you have, well, it's very wonderful, it's very impressive, but it doesn't tell you much about what's happening in this pile of yellow pads, which is where the proof took shape. You can ask mathematicians what happened, what they do, but obviously, self-reporting of that kind is, well, often, particularly if it's reporters trying to make TV shows, like this came through a TV show, they're focusing on the moment of inspiration. People want to think about the mathematician and the moment of inspiration, etc., etc. But actually, as we all know, there's a lot more than the moment of inspiration, and that's why this is a rather nice quote, because the first chunk is what one might call slog. And most of what we do most of the time when we're trying to prove things is slog. I don't know if people can translate slog into other languages. Slog in German, slog in Danish. It means working away very hard, so I used to try patterns, I tried doing calculations, I tried this, that, and the other. Sometimes I'd look at references, sometimes I'd tweak things a bit, sometimes I'd phone a friend, you mess around, you try things, work things out, see what's going to happen. And that process, at the top of the slide, is something that we don't understand terribly well, really, but that is perhaps, if you're looking for computer support, maybe that's the bit where the computer support is going to be more, don't leave the inspiration to happen, but support the dull bits. And one of the things that mathematicians have been trying recently is, if you like, sharing out the slog by developing new models of collaboration. This is an article from Nature describing an experiment led by Timothy Gowers, where a bunch of people collaborated on a blog to prove a theorem. Well, they succeeded in proving the theorem, but also it gave you something else. It gave you the story of what they did to prove the theorem. It gave you all the dead ends. And this is a quote from their article. Who would have guessed that the working record of a mathematical project would read like a thriller? Well, here's a chunk of the thriller. It's too small to see, really, but you can see it's blog comments and it's a discussion. Actually, this particular chunk is someone called ProCoS talking to himself. This proof that what he's done up above gives me something stronger. Whoops, I made a mistake. Oh dear, I really made a mistake. And then they've got a way of organising this on the blog, and here's somebody who's organising the blog saying, okay, let's try something different. But you have, they've done about 9 of these by now. All of this is sitting there on the web, Google Polymath and proof or something, and you'll find these things, and you too can share in the excitement of seeing what's going on. Well, Why I mention this is because what I want to do is to understand this process of creating proofs. And of course, what this gives you, what this thriller gives you, is exactly something to go away and look at, to find out indeed how proofs come about. And there are many different ways in which you can look at this thing. I'm fortunate in being able to work with a bunch of social scientists, in particular somebody called Donald Mackenzie in Edinburgh. Donald wrote a wonderful book called Mechanizing Proof in 2000, which is, it's about us. It's rather disconcerting, you know, to read a book. But what Donald was doing was going away and looking at a number of instances of computer proof, a number of controversies, like the controversy about the Viper chip, which he's looking at, one of the things he's interested in is this business of, you know, what counts as error, what counts as a proof, and he comes to the conclusion that ultimately it's a human decision to decide to trust the proof. I mean, in some of the was it in Jay's talk yesterday? Somebody was saying, well, you know, how do you really know? And Don's conclusion is, well, ultimately it's a decision of trust, but it's a decision of trust with a lot more information and a lot more work behind it than the original paper proof. But Donald also, you know, the next quote, Donald is really thinking about all of this informal work that goes on. And, you know, so, well, he's a sociologist, so he has to use words like transmaterializing. But what he's talking about here is the way in which sometimes an awful lot of what the slog is this business of trying something, thinking about it in a different way, tweaking it a bit. That's what he's talking about, tentative transitory marks, etc., etc. With a crucial stage of disorder. And I can't resist putting up this slide because this is a slide of somebody called Dan Grayson giving a wonderful, you know, it's a tour de force of old-fashioned blackboard work, as you see. What's he talking about? He's actually explaining his formal proof in homotopy type theory of something, but in you know, the good old-fashioned way of writing on a board and rubbing things out and saying, well, you could do it this way, but no, actually you do it this way because. And right up there, it is a wonderful example of the contingency even of formal proof, because what he's saying is, well, yeah, I verified this in Agda, but I use these settings and that compiler and so on and so forth. And then, you know, there was a question from me, an extremely technical argument with somebody in the audience about why you use those settings and not the other settings. It's all, it just brings to light the contingency of all this. And also, of course, the fact that we think about the formal, you know, the machine proof as an eternal, you know, it can be just as ephemeral as the paper proof. If you can't run the proof anymore, if you've forgotten the hacks, if you've forgotten. Okay, so this is a project where it's just started. I'm hiring, if you know anybody who wants to give up all hope of a serious job in a serious UK institution and come and work with me on sociology of proof, then dissuade them, because but there are lots of interesting things to be done here. Ethnography, modelling what's going on, because, well, what is going on when people are having these conversations on these polymath blogs? It's not a proof, but it's something. It's a conversation in a fairly structured way, and thinking about how you integrate proof and other tools into the workflow. I'm not going to stop because I have one more thing. This is a slide. This is the other thing that's consuming my life at the moment. Some of you know. This is a slide in neat, scratchy handwriting of somebody who's getting to grips with distributed laws. I had not, till somebody showed me, understood the sums where both the multiplication and addition signs were used, in consequence of which the former examples must have been wrong, as I thought they were as follows: 5 times 2 equals 10, to which I add 3 equals 13, multiplied by 4 gives 52, instead of 5 times 2 equals 10, to which I add 3 times 4 equals 12. There, this person has done lots of examples and got them right. Some of you know who this person is. Any guesses from, well, sorry, half of you know, half of you know.
David.
Ada Lovelace. It is Ada Lovelace. That is one of Ada Lovelace's papers in the Bodleian Library. She's about 11 at the time. It's her 200th birthday this year. You can come to an exhibition in the Bodleian Library at the end of the year, and you can come to a symposium on the 9th and 10th of December. And I'm feeling very excited because we just got email this morning saying that some huge complication about digitization has been sorted out. I put this here just for Cliff. This is even more amazing, actually. This is, well, what is it? It's obviously a notation of some kind. It's a design notation. It's a hardware description language. It's Babbage's hardware description language. It's Babbage's design notation. Utterly amazing. Mid-19th century, here we are. Small stereotype sectors, printing point of paper, inking roller, traveling inking roller. And you might say, well, what's going on here? Well, nobody's really sure. Babbage isn't here to tell us. He only ever really shared it with his long suffering draftsman. Babbage has very messy handwriting because this is draftsman handwriting. But there's a wonderful research project going on at Royal Holloway. Adrian Scott and Adrian Johnston and Liz Scott, who also have a project with Peter Mosses to do. What's the project called? Fancom, yeah. Are getting fascinated by this and telling us what it's all about. Right, I really will stop.
I think we should save some few minutes for discussions. It's just too wonderful. Please go on.
Any last questions? Okay, we will. Thank you very much. Very interesting.
It's so what this is, it's describing mechanical.